We now begin our discussion of continuous probability distribution functions, and in particular, we are going to be studying in depth the normal distribution. The normal distribution is incredibly important in our study of inferential statistics. So, first question, what do the following variables have in common? Heights of college-age men, carapace length of male eastern box turtles, systolic blood pressure of humans, and IQ scores of humans. What do those four have in common? You first might notice that each of these is a continuous variable, with the exception of the last one. Heights of college-age men, those are lengths. Lengths are continuous. Carapace length of male eastern box turtles, for the same reason, is also continuous. Decimals also make sense with systolic blood pressure, even though we don't typically use decimals. We certainly could, but pressure is continuous. And finally, IQ scores of humans. Technically, your IQ would not be represented by a decimal. However, IQ scores can be approximated by a special continuous probability function. Aside from being continuous, there is something else that these variables have in common. They all distribute in a way that we call normally. So we need to study the normal distribution because the normal distribution is a natural way that lots of different variables distribute in the real world. Let's take a look. Here is the normal distribution, a way that many variables in the real world naturally distribute. We want to study its features. First, the normal distribution is often called a Gaussian distribution or a bell curve. It's pretty obvious the reason why it's called a bell curve, because this curve looks somewhat like a bell. It's also called a Gaussian curve in honor of the person who found the equation of this graph, and his name was Carl Friedrich Gauss, hence the reason it's called a Gaussian curve as well. So you may hear me say normal, Gaussian, or bell curve. They all mean the same thing. Before we study its technical features, let's consider one of the previous variables and why you think it would distribute normally. Well, for example, IQ. IQ distributes normally along this bell curve because in general, in the middle, you've got most people, and then out on the extremes, you have really, really intelligent people, but there's not many, and then you have people that are really impaired, but there aren't many. Let's look at the technical features. First, notice that there is a vertical line of symmetry that runs down the middle of the curve, and right here at the middle is exactly the mean. In case you've forgotten, mu is the population mean, and sigma represents the population standard deviation. So right here along this vertical line of symmetry, we have the mean of the population. It also is the median and the mode of the population as well. However, you'll see why we reference the mean a lot more than we do median and mode. Also, the total area underneath the curve is always exactly 1. This should make some sense given that with a discrete probability distribution, the probabilities needed to add up to 1. So for the same reason, the total area underneath of this curve needs to be exactly 1. Also notice that going in both directions, whether you go to the left or go to the right, the function tends towards the x-axis right here, but it never actually hits or crosses it. And the final feature we are concerned with is this concept of inflection points. Each normal curve has 2 inflection points, and the essential idea of an inflection point is where the curve changes its curvature. So for example, between these 2 points, the curve is generally curving downward. If you're familiar with a parabola, it looks like a downward parabola right here. However, to the right of this point over here, notice it's got an upward curve to it. I know the curve doesn't actually go up to it, but this part of it has an upward swing to it. And so does this over here. It's got an upward. If you were to continue to draw a U, it would be an upward U. So it's like here you've got an upward U, a downward U, and an upward U. Where they switch its U shape, if you will, that's called the inflection points. We're not going to get into the precise mathematics of that. We just need to know roughly where the inflection points are. The key, absolute, essential feature with the inflection points, though, is this. The actual data value that corresponds to the right of the mean, specifically at the inflection point, is precisely mu plus sigma, where sigma is the population standard deviation. So this distance right here is precisely sigma, and this distance right here is also sigma. It's just sigma in the other direction. So you got Mu minus sigma gives you that data value. Mu plus sigma gives you this data value. Once this distance sigma is fixed, you could then get out to mu plus 2 sigma and mu plus 3 sigma, or the other way, mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. You will soon see that we are going to be very interested in finding area underneath the curve. There's a total area of 1, but perhaps we might only want to know, say, this area right here. So we're going to be concerned with finding areas underneath the curve, and technically, the equation of the bell curve is this right here. Notice it has sigma, the population standard deviation, and mu in it, as well as the special constants pi and e. This is a complicated formula. We are not actually going to ever use this formula to find any of the areas. You could, but you would need to know some calculus to do that. You will see how we'll find some area underneath the curve in a coming slide. Let's first practice what we just learned with a specific example. The Wechsler IQ test has a mean of 100 points and a standard deviation of 15 points. Also, as we saw from the first slide, the scores distribute normally. So that's why you see a bell curve here, because the scores distribute normally. In general, you have the bulk of people around here in the middle, around the average, and then you have some people down here and some people up here. But we can now be specific with numbers. Precisely what IQ score goes right here? Well, that's exactly the mean, and we already know the mean is 100, so let's write that in there. So 100 is the mean score of the IQ test. Where then are the inflection points? The inflection points, it looks like they're about right here and right about here. So let's actually draw in some dots. Right about here and right about here. And precisely at those points, something special happens. Those points here and here are exactly a standard deviation away from the mean. And the standard deviation is 15, so standard deviation above the mean would put you at 115, and a standard deviation below the mean would put you at a score of 85, since 15 less than 100 puts you at 85. Now, once this distance here is fixed as the standard deviation, which is 15, we can continue to write up new points along here. So if we go 15 above the 115, that'll put us at 130. Another 15 above the 130, that would put us at 145. Or going the other way, if we went 15 below 85, that would put us at 70, and 15 below 70 would put us at 55. So the area under the curve is essentially representing the percentage of people that have these IQs. So you can see most people have an IQ between 85 to 115, because this is where the bulk of this area is. Whereas very few have IQ above 130, because that's a very small area here, or very few have an IQ below 70, because there's a very small area over here to the left. In fact, we can be very specific about this area. There's a very special rule that applies specifically to the normal curve. It's called the empirical rule. It tells us that 68% of the data is found between one standard deviation to the left and right of the mean, is found within one standard deviation of the mean. So that means that there are precisely 68% of people have an IQ between 85 and 115. So to be specific here, 68% of people have IQ between 85 and 115. That's the meaning of this first percentage in the empirical rule. The second percentage tells us that within two standard deviations, there's a total of 95% of the data. So two standard deviations, and let's write in another color here, between 70 and 130, because two standard deviations to the right of the mean would put you at 130, two standard deviations to the left of the mean will put you at 70. What this is saying here is that 95% of the data is found here between these 2 points, two standard deviations away from the mean. So 95% of the data is found within, this should say within here, within two standard deviations of the mean. And you might be able to guess, this 99.7% here tells us the amount of data within 3 standard deviations of the mean. So we have 99.7% within 3 standard deviations of the mean. This is in general right here. If we want to be specific, that means 99.7% have an IQ between 55 and 145. So 99.7% of people have IQ between 55 and 145. We also could have written down that 95% of people have between 70 and 130. So this empirical rule applies to any normal curve with any scenario that uses the normal curve. There's another rule of thumb that was mentioned at a previous time, but I want to bring it back again now. Any data points that are outside 2 standard deviations of the mean are called unusual. Any data points outside 3 standard deviations of the mean are considered highly unusual. So it is unusual for someone to have above a 130 IQ or below a 70 IQ. It is highly unusual for someone to have an IQ above 145 or an IQ below 55. In fact, 145 is often roughly where people consider the genius cutoff. So above 3 standard deviations in IQ, you're talking about having potentially a genius level IQ. And there's very few people that fit that criteria.